Okay, now that we have a few relationships to relate electrical parameters, so for example, we have Ohm's law, which says delta V equals IR. Okay, the potential across a resistor is going to be proportional to its current and the resistance of the resistor. Okay. Well, I want to build off what do we remember delta V is? That came from an electric field. Actually, I'm sorry, it came from potential energy. And we have potential energy was, like a change in potential energy was some charge times some change in potential. Okay, that's where our delta V came from. Well, what is the power dissipated across a resistor? So a resistor takes energy out of a light bulb, converts electrical energy into light energy. So what's the power? At what rate is that energy dissipated from electrical energy to light or other form of energy? Well, power is defined as the change in potential energy over the change in time. Okay. Now this du is a small change in energy, in the small change of time. And that's basically saying how many charges did I move across this potential. Potentials are usually fixed. Okay, they're fixed. They don't change in time. This is a battery has a certain potential, it's fixed. But the amount of charge that gets pulled across that potential or given potential energy through this potential can change in time. And that's our current. And so this could be written as dq delta V over dt. All right. And what's cool about that is dq dt, since potential is fixed in time, it doesn't change in time. dqdt is our definition of current. That is current. So we have I delta V. So we have this relationship that the power dissipated, or even the power provided by any potential source, so it's provided by a battery or it's dissipated across a resistor, is given by the current times that potential difference of that device. If we combine it, so this is a really good relationship, helps us to understand that. But if we combine it with this, we can write it in different ways. If I replace IR with delta V, I get I squared R is one way to calculate it. So if I know the current and I know the resistance, this would be the fastest way to calculate the power. I could also replace I through Ohm's law, do I equals delta V over R, and I can get delta V squared over R. Okay. And in these different ways, we can figure out, well, how is the power dissipated changing with the different things that I might be in control of. And we actually apply this idea to very long power lines. The resistance grows with length, and so we want to try and minimize the amount of power or energy that's lost because of the resistance in the power lines. And so by changing how much or decreasing the amount of current that's flowing by increasing the potential allows us to minimize the effect of that increasing length. So anyway, these are all three different ways of looking at power. Now, there's the unit for power is watts, joules per second, but there's a really unique power unit or energy unit used in the United States called the kilowatt hour. So like if you buy energy in the United States, you buy it in terms of numbers of kilowatt hours. Okay, now remembering that power is energy per time, and power is measured in watts. A kilowatt would be an energy per time. So a kilowatt hour, which is given kWhr, that is the unit for energy in electrical or power providers in the United States. This is energy per time, and this is time, which means energy per time times time I get energy, which is what this unit is. Now it's kind of weird. So for example, what's 1 kilowatt hour in terms of SI units, in terms of joules? So 1 kilowatt hour is the same thing as 1 kilowatt for 1 hour. Okay. Now 1 kilowatt is 1 kilojoule per second times 1 hour, which is 1 kilojoule per second times 3,600 seconds. And so the seconds now cancel, and we get 3,600 kilojoules, okay, which is 3.6 times 10 to the 6th joules. So 3.6 million joules. That's how much energy is in a kilowatt hour, 1 kilowatt hour. Now, what's interesting is the joule is actually not that much energy. But what's even more amazing is that the cost, general cost in the United States is, anywhere from 10 cents to less energy or cents per kilowatt hour. And so a joule really is a really cheap amount of energy, a really small amount of energy. And because it's in terms of joules, it's so high. So this is just kind of an FYI to understand what kilowatt hours are. But this is the idea of power. It's proportional to current and voltage, or current squared and resistance, or potential squared and resistance. This is the power provided by a power source, or it's the power dissipated by a resistive source, a load.